Hello and welcome to the next topic in our discussion on hypothesis testing and the t-test in particular. We're just going to run through a couple of examples to demonstrate the slight variation between the single sample t-test and the next one. So the main question, or the basic question, is looking at husbands and their communication skill or quality with premarital counseling. So we are looking at a baseline of husbands whose communication quality does not change from before or after marriage, and then those that get counseling to see if that does have an impact, a significant impact. Does it change? We don't know if it's better or worse, but we're investigating a change. So we could rephrase this. Let me zoom in on this. If we look at this comparison distribution, sorry, I was just looking at what I just covered, thinking I need to cover the comparison distribution, and then I messed it up. If I look at the hypothesis, null hypothesis and research hypothesis statements, I can phrase them. Oh, it's a little thick on the pen here. Let's just go a little thin. That's better. I can rephrase this as saying H1 minus mu1, I don't know what's wrong with me, mu1 minus mu2 equal to 0 as the null hypothesis, mu1 minus mu2 not equal to 0 as the research hypothesis. And in that way, I can still view it like I did before. Even though now I'm comparing two means to see if they are the same or different, I can rephrase this to compare the difference of the means to, in this case, a number of 0. So that is exactly what we're going to do, and it's really that simple. We're going to look at the before and after scores, and we're going to calculate the difference scores, and that'll be what we're focusing on. Because essentially what's happening, I'll write it at the top here. If we have two distributions, I don't want to say distributions, but if I have two, I'll say distributions, yeah, the before and the after. They're the same people, so they have the same variance. If each one has a normal distribution or a t-distribution or whatever, the difference has the same distribution. The difference we choose before minus after, that as a random variable has the same distribution in terms of its mean will be the same as the before minus after mean. Its variance will be the same as the before and the after variance. So the variance is a little different. We don't subtract those. The variance is the same throughout. So if we look at the difference scores, we can analyze the situation and see, does this difference mean, I guess I'll put a D there, how does that compare to 0, essentially? Okay, so that's what we're going to do. Calculate all the difference scores here, and then we want to calculate the deviation from the mean. We calculate the mean here. Let's see at the bottom here. It's a little small. Let's see if we can zoom in. At the risk of covering it up over here, that's okay. We're looking at the mean, negative 12.5. by adding up all the difference scores. This is now specifically difference scores. Everything's going to be done with the difference scores. Calculating the deviation from the mean, sum of the square deviations, then we can calculate the sum of the squares as soon as my laptop decides to shift the page. Now the laptop is a very moody thing, very moody. But you know what, laptop? I can do it myself. Whoops, I went too far. Apparently I can't do it myself. I thought I could. Turns out I cannot. I'm trying to swipe this thing. There we go. There we go. We calculate the sample mean of difference scores. We calculate we estimate the variance because we do not have the population variance, population of difference scores. So again, we have 19 of them. We divide by 19 minus 1. Sample size minus 1. We get the same, the comparison distribution, we get it in the same way. The distribution of means, we get the standard error. So we want to remember this guy and, well, we're testing it against 0, I guess. But for our sample, it might be drastically different. The mean sample difference score we want to remember over here. So let us go back to the first page. Might be a little zoomed in. We'll see how it goes. So now our comparison distribution is from population 2, but thinking about differences will be when there's no change, which means the mean difference is 0. Sigma was unknown, so we used our sample to calculate to estimate it, and we get our 2.84 like we just showed here, right? It is a t-distribution. Degrees of freedom is 18 because our sample size is 19, and degrees of freedom is 1 less. All right, so far so good. Now we're going to do the same thing as we did before, but we are looking at differences. So we're looking at mean here of 0. And I don't know why my pen is so thin. Maybe that's better. 0 mu. And we're seeing, well, what did our next page? Nope, apparently not next page. There we go. What did our, oh, actually on this slide, before we go to our sample, we determine what will our cutoff be. So we're choosing an alpha of 5%, two-tailed, because we're only checking is it the same or different. T-distribution, degrees of freedom 18. So if we visualize that, just like always, I'm going to have 2.5% in the tail on each side, 2.5%. We go look in our two-tailed T distribution table, 5%. Now I have to go see the degrees of freedom was, I think it was 18, right? 18, and I get here 2.101. 2.101 and negative 2.101. That was on the slide. 101. Good. Then we see Okay, well, what does our sample tell us? Our sample, remember, negative 12.5. We found 0.5. We found that over here from our difference scores. That's our sample mean, negative 12.05. We calculate that in the same way we do the t-score. I'll show you in the formula sheet here, over here, t-score, single sample, but now having merged the before and after scores, we're back to our single sample situation. That's the beauty of it. Plug it into the formula, we get negative 4.24. Negative 4.24. Ooh, that is, let's put that over there. So this is T cutoff, T cutoff, and this will be, let's give ourselves some space, T observed. What did I just say? Negative 4.24. Negative 4.24. That is beyond the cutoff, and we therefore say that this is strong enough evidence to suggest that the difference between the two means is not 0, which means there is a difference in the effect. Well, I shouldn't say effect, in the effect of counseling. The score, negative 4.24, is more extreme than the cutoff. Therefore, we reject the null hypothesis. The research hypothesis is supported. The husband's reported communication quality, I don't want to say decreased. All we are testing is for a change. So let's say changed. We can then rerun the test if we want to see a decrease, because the alpha was different in a two-tailed test. We lost half of it to the other side. So the evidence suggests that the counseling does change the husband's communication skills. All right. So let's do one more. Actually, let's run through the summary and then emphasize it with another example. So I'm going to zoom in here since we can squeeze it, I think. So the steps for a t-test for dependent means. So dependent means it's the same people, for example, before and after some sort of treatment or test. Counseling was the treatment. The husbands were measured before and after, and we're investigating some sort of change. We can rephrase the research and null hypothesis in terms of a difference. So we're looking at difference scores. And then everything is pretty much the same. We get the mean. We look at the distribution of means. And under the null hypothesis, this is going to, the population 2 is going to have a 0 mean. Then we have to estimate the variance of that distribution because it wasn't given originally. Same as before, degrees of freedom 1 less. Everything is the same now. Determine the cutoff, decide significance level, one-tailed or two-tailed test, look it up in the t-table, use your formula over here, that's the same, and make your conclusion. So let's have a look at another example. And we can ask a question like, are students in this class closer to their mothers than their fathers, for example? So population 2 will be people, or the baseline, so to speak, people who are equally close to both parents. The mean difference is 0. Or population 1, sorry, I have to rephrase this. Population 1 will be what we're looking for, what we're hoping for. So let's see here. Oops. Of course, the pen doesn't want to work with me when I need it. Let me just double check if the pen wants to be my friend. Closer to mothers. And then here I'll just say not closer to mothers, just to have everything match up with this phrasing over here, which I'll zoom in on. Whoa, random line. I'll zoom in here. So the null hypothesis is that they're not closer to their mothers. The research hypothesis that they are. Now we can of course rephrase these h1 sorry, I keep saying h1, mu1 minus mu2 less than or equal to 0, mu1 minus mu2 greater than 0. We are looking and hoping for mu1 to be greater than mu2, the closeness measure to mothers more than to fathers. In other words, the difference positive versus not. Okay. Zoom out a little and have that over there. So then we can go and take our sample, and our sample has 109 students, measuring the closeness to each. It's the same student. So we can calculate the differences, sort of a before and after situation, but not quite. We can still look at differences because it comes from, the two sets come from the same people. And we get these difference scores, and from them we can square them and estimate the variance, of course. So we get the mean difference here. And if we keep calculating, we get the estimate for the population, the difference population variance. Our comparison distribution information is over here, mu0 under the null hypothesis, and our error of the standard error is over there. And the comparison distribution will be a t-distribution, degrees of freedom 108. All right, so that's our setup. Let's see what we get, what this sample is suggesting. So we have our information here just like we saw. Let's perhaps first visualize this over here. 0 there. Oops, now my pen is super small. If I write on the slides, the standard pen is very, very thick. And then I move to a normal page and it's super thin. Okay, so it's going to be a one-tailed test in this case, right? Because we're only interested in investigating if students are closer to their mothers, hence the inequality here. So we calculate, let's say alpha is 1%, one-tailed test. Let's indicate that first. Let's put 1% over here. 1% on this side because this is the difference mother minus father. And we're hoping for positive, right? So we want our t cutoff. 1%. Look at the table. It is a one-tailed test. Look at the tail, 1% column over here. We go all the way down. Oof, over 100, 2.327. 2.327. Let's see what they have over here. I changed this, which is why I wrote stuff in here. I wanted to have a one-tailed test in my video. So then we look at the sample mean of differences we got, 1.44. Is that what we got? 1.44 over here. Then we have to convert that to its corresponding t-score, which I'll call t observed, and we get 6.26. Let's write that in. Oof, that's way out there, right? T observed 6.26. And we therefore conclude that this observed score from the sample is more extreme than the cutoff. Therefore, we reject the null hypothesis in favor of the research hypothesis. Students in the class have are closer to their mothers than to their fathers, or the evidence at least suggests that. Okay, so everything is very much the same, except if we have a before-after situation, or we have two sets of scores in our sample coming from the same people. We call that a t-test for dependent. Dependent means the mother-father scores, they depend on each other. They're connected to each other. Because different people have similar scores and similar views. Sorry, what did I just say? Different people? No. The same person has, the scores are in line with that person. Another person has, it's the same information. Well, let me rephrase that. It's the same person's information, two sets coming from the same individual. And because it comes from the same individual, the variance between these two sets, these two samples, are the same, and that's why the distribution of differences can be looked at. So I want to always I want to think and ask first, where is the sample coming from? Do I just have a single sample that I'm measuring against some value in terms of the mean? I'm measuring the mean against some value. Or do I have two sets of values? Two sets of sample values that are somehow linked and connected to each other. Then it might be a t-test for dependent means, but it's very similar, and we convert it to a single sample t-test by looking at the difference scores instead. All right, that's it for this video. We'll wrap it up with the next one, looking at the last variation on the t-test. Until then.